Welcome back, students. We went through an example problem on matrix exponential. We went through this matrix and we used just brute force computation to find that I, AT, A squared T squared, A cubed T cubed, and so on with all those factorials in denominator, like this kind of computation. And then we ended up with this. Let's explore another problem, but in the same method. Okay, here we go. We have matrix B, and then we want to find out e to the bt power. Same Taylor-Maclaurin series expansion, and we want to find out I and b, of course, there, b squared t squared, b cubed t cubed, b to the fourth power, t to the fourth power, and so on, and we are trying to find out some pattern. Okay, here we go, and here's the computation. And speaking of pattern, I use this color coding to emphasize this pattern here. Please pay particular attention to this 1, 2 entry, upper right hand side corner. I, okay, no problem there, 1001. B, that's the definition, and b times t, okay, there you go. First line is no big deal, as usual. Now let's find out b squared. So this is b times b, and first row, first column. So 1 times 1 plus 1 times 0, that's 1, okay. First row, second column. 1 times 1 plus 1 times 1, we get 2. So times t squared, we get this matrix. That's b squared t squared. And we're going to divide by 2 factorial later on. How about t cubed? This is b squared. And then first row times first column. 1 times 1 plus 2 times 0, that's 1, no problem there. First row, second column. 1 times 1 plus 2 times 1, and that's 3. And multiplying t cubed, we get that. How about the next? This is t cubed, and first row, first column, 1 times 1 plus 3 times 0, that's 1, no problem there, but 2 to this one. 1, 2, and 3. First row, second column, 1 times 1 plus 3 times 1, that's 4. And then if I do this again, 1 times 4 times 1, 1. So 1 times 1 plus 4 times 1, that's 5, and so on and so forth. You see the pattern, I guess. Arbitrary k comes here. Upon multiplying t to the k power, we get these matrices. And that's the general pattern. Make sense? Okay. Now let's add those up with appropriate factorials to divide. And it's t here. Now, how about this part? 1, 1, and 3, let's see. 1 t squared, t cubed, t to the 4th power, 5th power, 6th power, 7th power, arbitrary k power. No change from the original definition of the exponential function. And of course, denominators are all factorials. So clearly, this whole thing will give me e to the t power. Just by looking at 1, 1, and 3, no problem there. And 2, 2, and 3, exactly the same deal. I don't have to even think about 2, 1, and 3. Now 1, 2, and 3 here. Oh, that's important. So let's scrutinize this one. First, we begin from 0. Okay, 0 times t to the 0 power, so this part actually drops out. Okay, that part is actually 0. And then we have t over 1 factorial, 2t squared over 2 factorial, 3t cubed over 3 factorial, 4t to the 4th power over 4 factorial, and this times 5 factorial, and so on. You know, factorials are embedded originally from the definition down here in the denominator. So what you end up with is k over k factorial. So that's 1 over k minus 1 factorial. You see, k factorial means k times k minus 1 times k minus 2, k minus 3, all the way go down. Numerator is k, so the top number is dropped down. So we have all these. You see that part, which I put those background color in, that's 0. And all these here, those are after simplification, k minus 1 factorials. So we have 0 factorial, 1 factorial, 2 factorial, 3 factorial, and so on. We just got a reduction. The powers of t's, on the other hand, they are remaining the same. T to the first power, second power, third power, fourth power, and so on. So it's the same as t times e to the t power. You see, factor t out, then we have 0 power, first power, second, third, fourth, and so on. So we successfully identified e to the bt power. It's this one. E to the t power, t times e to the t power, 0, and e to the t power. By the way, this kind of matrix is that's an important class of matrix actually. This is one of those examples of Jordan canonical form. And one may come here or down here, and this one will become 0. Either way, Jordan canonical form. We may come back and discuss those and use that term in lesson 15. Okay, all right. We went through these matrices. Now, before moving on to the next topic, let's go back to the motivation. Why did he discuss these matrix multiplications, or matrix exponentials to begin with? Remember, this was the reason. Homogeneous system, and then if you add a particular solution, then you're going to get solution for non-homogeneous system. Turns out like this, and this is a homogeneous part we saw, and then this is non-homogeneous part. We're going to discuss those in lesson 14. Let's stick to homogeneous case. Exponential times the initial value condition, initial condition. Okay, all right, there they are. So the first problem here is associated to this matrix. So this matrix is being applied here. So the answer must be e to the at power times the initial condition. That's gotta be the answer here. That's the solution. And what is this e to the at power? Well, that's the e to the at power we calculated in the previous example. So cosine, sine, negative sine, cosine times this initial condition. We end up with this solution. So x of t is negative cosine of t plus 2 sine of t, and y of t is sine of t plus 2 cosine of t. So we solve the system of first order linear ODEs. And how did we do that? The key computation was matrix exponential. How about the next problem here? And the second problem is associated to this matrix. So we're going to do the same thing, e to the bt power times the initial condition. Indeed, this is a matrix computation we have to do. And we found out e to the bt power is this. Remember? So this matrix times the initial condition, well, here's a matrix computation. So what do you end up with? X of t is negative e to the t power plus 3t e to the t power. And y of t is 3 e to the t power. And there goes the unique solution. The unique solution given by the equation, the ODE, and the initial condition. And that's how you can do it. So calculating the matrix exponential is actually an important, very, very important step. That's nearly all the problem there is, as a matter of fact. And after that is done, this matrix multiplication is just one further trivial step. So my analogy may be calculating the matrix exponential is scoring a touchdown, and then getting the final solution here is just extra score. So we went through the matrix exponential here, and we're going to study more matrix exponential in lesson 14. Here in lesson 13, we're going to stick to various preparations. And this concludes 13a. In 13b, we're going to talk a little bit more about determinants and some other stuffs. They're not that important.